In the past few years, there has been a marked change in the development of space launch systems. No longer can the unsophisticated low-thrust launch system perform the increasingly complicated research mission in space. The development of today's launch system requires a combination of the most advanced concepts from science, management, and manufacturing, and on a gigantic scale. Two of the United States' most successful launch systems have been developed by Douglas. These are the Delta program and the Saturn terminal stage program. Douglas had a long record of experience in launch system development and flights with cryogenic propellants, and an equally successful record of prime systems management. Douglas recognized that systems management was the key to the success of any program of such magnitude. For this reason, one of the most important tasks was the establishment of a smoothly working relationship among the customer, the prime contractor, and the subcontractors. Then, to develop launch systems, special facilities had to be acquired or constructed, including vast amounts of floor space for management, for research laboratories, for engineering, for manufacturing, and testing. At Huntington Beach, California, for example, the Douglas 245-acre Space Systems Center will soon have 2 million square feet of floor space. Special test facilities were constructed, such as a liquid nitrogen-cooled 39-foot in diameter space vacuum chamber, capable of producing an operating pressure of 10 to the minus 9th power torr at a temperature of 100 Kelvin with a 300 kilowatt thermal load. A 5-place heavy-duty structures test facility with each place capable of reacting 1 billion inch-pounds of moment and 1 million pounds of shear. A liquid hydrogen research and testing complex. A 4,000-acre complex for test firing and checkout of liquid hydrogen fueled propulsion systems and complete stages. A smaller 3-position complex for the testing of hypergolic propulsion attitude control systems. And a 2-position post-firing vehicle checkout facility. These are but a few of the 100 research, development, and testing facilities employed by the Douglas Missile and Space Systems Division. While the development of advanced space research systems requires extensive pioneering in many fields, a high degree of reliability can only be assured by drawing upon experience acquired in previous programs. Such was the case with Delta and with Saturn. Thor, now with more than 200 launches, provided a comprehensive background in the use of cryogenics. Designing for cryogenic propellants was not new to Douglas. What was new at that time was designing for the use of liquid hydrogen in conjunction with liquid oxygen, while maintaining the extremely high degree of safety required for launches. Extensive research was required in the development of designs for liquid hydrogen containment, for liquid hydrogen thermal insulation, and for structural stresses under conditions of extreme temperature gradients. Development of the S4 stage common bulkhead, for example, was a major achievement. This structure forms a common bulkhead between the liquid hydrogen and liquid oxygen propellant tanks. The Delta vehicle pioneered the use of liquid-propelled first and second stages, coupled with a solid propellant third stage. Working with the manufacturers of diverse types of spacecraft required a degree of cooperation never before achieved. The Delta program is a good example of mission-to-mission variations required of modern launch systems, with each mission presenting unique problems. At the Douglas Aerophysics Laboratory, aerodynamics tests were conducted for a recent mission in the hypervelocity impulse tunnel to determine the heat transfer rates on the Delta launch vehicle at unusually high angles of attack. As a result of these and other tests, the Delta vehicle was provided with special heat insulation for this mission. The manufacture of space vehicles presents a number of problems. In order to work the special materials at close tolerances, numerous unique tools and fabrication processes were developed. One of the most important contributions these two programs have made to the space age is the low-risk ground test program. In itself, testing is nothing new. What is new is the magnitude and stringency of the Douglas program. Basically, the philosophy is that the acceptability of every critical component, then of every system, must be demonstrated by complete performance while operating under conditions simulating the launch and space environment. The tests range from the smallest of the solid-state devices to testing of individual systems, and finally, testing of combined systems. Reliability assurance in itself is a complex program, and as systems become more sophisticated and more expensive, reliability and quality control become increasingly important. To the already comprehensive ground test program is added reliability testing and individual component investigation programs. Survey teams are sent to subcontractors to assure their compliance with assigned specifications. On flight-critical items, these contractors are required to set up and conduct their own quality control and reliability programs. While the flight systems are being developed, an almost equal amount of effort is expended on the design and development of ground support equipment. In order to assure the desired confidence for manned launches, nothing short of completely automatic checkout was acceptable. A special laboratory facility was constructed in order to test the integrated operation of the entire automatic checkout system, in conjunction with a simulated S4B stage. This simulated stage is provided with all actual or simulated components and systems of the stage. The record of both the Delta and Saturn vehicles indicates that these programs have been successful. Out of 30 missions conducted to date by the Delta Space Research Vehicle, 28 have been successful, giving the three-stage Delta a long-term reliability record of 93%. This record has been achieved during a period in which configuration changes have more than tripled the original Delta mission capability. Even further improvements are now being studied, including the use of fluorine propellants. 4 Saturn I vehicles have been launched to date. All have been unqualified successes. When the Saturn V vehicle is operational, the Douglas-built liquid hydrogen-fueled S4B stage will be required to operate after a long zero-gravity orbital coast. There is an expression that says, the road to space must be paved with experience. In retrospect, the requirements of these unique programs forced pioneering in many fields: in management, in design, in manufacturing, in testing, and in support equipment. The proven success of these programs has provided Douglas with a unique pool of 23,000 employees, highly experienced in the development and launching of space vehicles. Virtually every space research launch conducted by the United States adds to the wealth of Douglas experience. Form the increasingly complicated research mission in space. The development of today's launch system requires a combination of the most advanced concepts from science, management, and manufacturing. In the past few years, there has been a marked change in the development of space launch systems. No longer can the unsophisticated low-thrust launch system Douglas had a long record of experience in launch system development and flights with cryogenic propellants, and an equally successful record of prime systems management. Douglas recognized that systems management was the key to the success of any program of such magnitude. For this reason, one of the most important tasks was the establishment, and on a gigantic scale. Two of the United States' most successful launch systems have been developed by Douglas. These are the Delta program and the Saturn terminal stage program.